Okay.
Hello, everybody. Welcome. I'd like to introduce Dan Schwartz. He's a soil scientist with the Northern Virginia Soil and Water Conservation District. He's experienced with identifying and mapping soil types, erosion and drainage issues, and stormwater control. He is a frequent speaker not only for TreeStewards, but for community and school groups. Welcome, Dan.
Thank you, Terry, and good to see everybody tonight. So as you might guess from my official title, soil scientist, we're going to be talking about soil tonight, which, of course, if you are interested in growing healthy trees, you do need to have good soil to begin with. It's kind of the base of everything. I will share my screen and pull up my presentation. Hopefully it's showing up for you all.
We see it, or
Great.
I see it.
If anybody has any problem seeing it or hearing me for any reason, just chime in and tell me, and I'll hopefully fix it. But assuming that there's no problems, we'll go ahead and get started. Yeah, so we're going to be talking about soils today, and specifically about soils and urbanization, the effects of urbanization, because whether you live in Alexandria or Arlington or somewhere outside of there, chances are you live in a fairly developed area of the state. All of Northern Virginia's got pretty dense development, and that development is spreading wider and wider as we speak, pushing out into Loudoun County and Prince William and Stafford and all the surrounding areas. And when development comes, it changes soil significantly, mostly, unfortunately, for the worse. But we'll talk about some of those changes, and also we'll talk about, not to be too depressing, some of the things that we can do to alleviate some of those negative effects of urbanization. So let's go ahead and get started. Now, I like to start off by basically kind of going over a simple question. What is soil? Soil is really a combination of solids, liquids, and gases. And that's makes a little bit of sense, but generally when we think of soil, we think of it as a solid. I mean, you're sitting in home, your house is sitting on top of soil. The trees out in the backyard are anchored in soil, and we get a good windstorm and maybe a tree or two will fall here or there, but for the most part, that soil has enough strength to keep everything standing. So it's not a mystery why we think of soil as a solid, but we tend to discount the importance of water and gas in the soil. We also tend to discount how much is actually in there. So if we look at healthy soil, and I put the emphasis on healthy because, again, not all of our soil around here is healthy. Healthy soil is about 50% solid material by volume, 25% gas, or what we call the soil atmosphere, by volume, and the remaining 25% is water. So a quarter of our soil volume in healthy soil is gas, a quarter is water, and 50% is solid. We want to break it down even a little bit further. 5% of the soil is organic matter, and 45% is solid mineral material. So we got 45% mineral solids, 5% organic solids, 25% gas, and 25% water, making up the recipe for our healthy soil. And again, that's probably quite a bit more than you may have suspected. But yeah, healthy soil is actually 50% open space that can be filled by either gas or water. Let's look at those soil solids a bit more. Even though there's less solids in soil than we might have originally thought, they're still very important. And really, when it comes to the human tendency to want to categorize things, it's this type of soil, it's that type of soil. When we're categorizing soils, we really are categorizing based upon the different types of solids from spot to spot. So again, mineral fraction is 45% of the soil volume. What is the mineral fraction made up of? Very simply, it's sand, silt, and clay, those three particles. The organic fraction, 5% of our soil by volume, is composed of both living organisms, so what's alive in the soil we consider to be part of the soil, and dead organisms, dead decomposing organic matter. So that mineral fraction, what is a particle of sand? What is a particle of silt? What is a particle of clay? It's a bit of a loaded question because within each of these three categories, sand, silt, and clay, there are lots of different types of minerals. You can have sand from a variety of different bedrock. As bedrock breaks down, it can create sand. You can have silt with a huge variety of chemical formulations or of crystal structures, clay as well too. So there's a lot of different types of sand, a lot of different types of silt, and a lot of different types of clay. It's not to say that there's no variation within each of these three categories. But for our purposes, just looking at sand, silt, and clay as these large groups of organisms, of molecules, what separates sand from silt from clay is simply particle size. So you can have a particle of soil that's made up of exactly the same chemicals, the same atoms. And if it's a little bit larger, it would fall in the sand category. If it's a medium-sized particle, it'll fall in the silt category. And if it's a clay-sized particle, if it's a very small particle, it'll fall in the clay category. So calling something a sand or silt or clay doesn't necessarily mean you're talking or making a comment about the chemical formula, the chemical makeup, the atomic makeup of the particle. All you're talking about by classifying something as sand, silt, or clay is making a distinction of the particle size. So there's a couple different ways to categorize sand, but generally as tree stewards, as people interested in ecology and in the environment, we use the U.S. Department of Agriculture's classification system. The other classification systems are more for engineers and builders. But USDA says that a mineral particle between 2 and 0.05 millimeters in diameter is sand. A mineral particle between 0.05 and 0.002 millimeters is a silt, and anything less than 0.002 millimeters in diameter is clay. And again, remember, there can be plenty of different types of sand, silt, and clay, but the difference between these three categories is just differences in particle size. So this illustration does a pretty good job of showing the relative differences in sand, silt, and clay. So even though these are all very small particles to us, sand is a lot bigger than silt, silt is a lot bigger than clay, and clay is very, very, very tiny. So all clay is microscopic, and in fact, you need a pretty powerful microscope, like an atomic microscope or an scanning electron microscope, in order to see an individual particle of clay. You need a microscope in order to see all particles of silt. And sand kind of bridges the divide. Those larger particles, 2 millimeters in diameter, certainly you can see that with the naked eye. When you get down to 0.05 millimeters, we're getting into the microscopic range, though. These distinctions are a little tough. I mean, what does 0.002 millimeters really mean? Obviously, that's very small, but that's the same as saying 2 microns. So a clay is any particle less than 2 microns, and a micron is a millionth of a meter. So if you think of that slightly larger than 3-foot long meter stick, if you were to slice that into 1 million equal parts and put 2 of those slices together, that would be the diameter of the largest particle of clay. And they can get quite a bit bigger than that too. It's quite a bit smaller than that too. I was listening to a master gardener give a presentation many years ago, and I thought she had a really good analogy for how these things are different from each other. She said, if you're ever driving to a Commanders football game, the stadium is analogous to a particle of sand, your car in the parking lot is analogous to a particle of silt, and your parking pass on your windshield is analogous to the particle of clay. So that gives you a pretty good idea of the relative differences in the sizes of these three particles, even though, again, they're all fairly small by the human scale. Now, the reason that sand, silt, and clay is important is that they determine something called the soil's texture. It's one of the big, important physical characteristics of soil. And texture is very simply the percentage of sand, silt, and clay in a soil. So if you pick up a clod of soil from your backyard, spray it with a little bit of water, work it up in your hand until you get a nice kind of putty-like consistency, and it's a really sticky, dense kind of feel to it. That would be a clay soil. It has a clay texture, high percentage of clay. If your soil after wetting feels very gritty and hardly adheres to itself at all and just makes a big mess on your hand, that's going to be a sandy soil. And a silty soil is kind of like a powdery feel, almost like a talcum powder or a baby powder or even foundation makeup. Generally, we will never really find pure sand, pure silt, or pure clay around here. It's always going to be a little bit of a mixture of all three. But certainly some people have much sandier soils than others. Some people have silt-dominated soils, and some people have clay-dominated clay-dominated soils. And then there's quite a few of us who have a fairly even mix of all three, and we would call that a loam. Texture is important because it really helps determine the ability of the soil to both hold on to water and nutrients, but also to allow oxygen and water from the surface to pass down into the soil and into the rooting depth. So the organic fraction, and again, this is only 5% of the volume of the soil, so it's pretty small, but despite being a very small percentage of the soil's volume, it's very important for the health of the soil. And it consists of two things. The first one is living material. So anything alive in the soil, oddly enough, we consider to be part of the soil. So your groundhog or your fox, they're sort of in and out of the soil. So sometimes they're part of the soil when they're in their dens, otherwise they're up on the surface, they're not part of the soil. But some organisms, living organic material that you might be a little more familiar with and think a little bit more of as a soil organism would be, our standard earthworms, all the little insects, some macroscopic, some microscopic, that work their way through the soil and the forest litter. And then the stuff that we can't see but are present in huge, huge numbers in the soil, that would be the soil fungi, and the soil bacteria, and then the soil fungi. It's estimated that every teaspoon of healthy topsoil has anywhere from 100 million to 1 billion bacteria residing within it. And that same teaspoon of topsoil can, for fungi, we measure the length of these fungal roots. So these little microscopic fungi exist in the soil as these little tiny, mostly microscopic root hairs, basically little white twine that work their way through the soil. If we could take those little root hairs of fungi from 1 teaspoon of topsoil and lay them end to end to end, we'd find that they'd stretch anywhere from about 40 yards per teaspoon to 40 miles per teaspoon. So we're talking about a tremendous amount of living material in the soil, most of it microscopic and invisible to us. But that's not the only thing that's in the soil. There's also the dead organic material. And this is equally important because this is the food source for all of the living material. So the living material are feasting on this dead material, breaking it down and releasing nutrients, both for themselves and out into the wider soil ecosystem. So that is our soil solids. And then we go on to our air and water. And it's not quite as interesting as the soil solids and the organic matter and such, but it is interesting to talk about because when we're talking about soil air, what we call the soil atmosphere, and soil water or groundwater, it's not exactly the same as our surface waters and the atmosphere that we're breathing right now. For the most part, once it gets into soil, the air and water is more heterogeneous, meaning there's a lot of variation in what makes it up based upon the space that you're in. In soil, you've got a lot of little defined pockets of open space that can be filled with air and water. And sometimes those pockets are attached to the surface through a nice pore space. Sometimes they're really cloistered and kind of segregated. The more segregated ones tend to have very different air and water types than we would see up at the surface because they're kind of isolated from their surrounding areas. Whatever biological activity is occurring within that isolated little pocket will really change the chemistry of the air and water. Perhaps, if you've got an isolated pocket with some organic matter that's being decomposed, all the oxygen might be used up out of that little pocket of air, and maybe it's all full of carbon dioxide. That could also make the water in there a little bit more acidic as the oxygen in that little isolated pocket becomes more and more carbonated. Some of that carbon dioxide dissolves in the water and becomes carbonic acid. So these are just not things that you really have to concern yourself with too much, but just know that the air in soil is not the same as the atmosphere above our heads. And the water in soil is water, but it tends to be more variable in its pH, in its chemical and mineral and dissolved material content. And again, that variation is highly dependent on the activity of the surrounding soil organisms, those living organisms, bacteria, fungi, the little insects and worms. But generally speaking, if we were to say, there's a general rule about the differences between what's in the soil and what's above, is that there's going to be a lower oxygen content under the soil. It's certainly not going to have the same concentrated oxygen content as the air that we breathe. So in your nice, natural, fairly healthy soil, this division of solids, liquids, and gases is a sign of healthy soil because it really gives plants what they need. You need enough solid material for physical support. So if we had a soil that was, let's say, 50% water, 25% gas, 25% solids, you try to grow a sycamore or any other large canopy tree on a soil like that, chances are every big windstorm, you'd be losing a good portion of those large trees just because there wouldn't be enough physical support for the roots to hold those big trees up. But you also need enough water and air in order to keep the roots healthy, the plant hydrated, and to get adequate nutrients down into the soil. So, what happens to your potted plants at home if you don't water them enough? And they start wilting and then eventually they die. But, if you water them too much, what happens? Their roots start rotting. So roots need oxygen. They breathe oxygen just like we do. The leaves take in carbon dioxide, but the roots take in oxygen. But they also need plenty of water, both to keep themselves upright and erect, to prevent wilting, but water is also the medium by which they take in their nutrients. So roots are never taking in anything solid from the soil. They're never absorbing little particles of soil. They're never absorbing little solid particles of organic matter. Rather, they're taking in plenty of nutrients from the soil, but those nutrients first have to dissolve in the soil water. And when the plants go to drink, they're taking in the water, but they're also taking in those nutrients dissolved within the water. So water is kind of of double importance to plants because it obviously provides them the liquids that they need, but it also provides them a medium for dissolved nutrients to get into the plant and power new growth. And when you have a soil that's 50% solid, 25% gas, 25% water, you've got a very good chance that you're giving the plant what it needs. Enough solidity to keep it upright, but enough soil atmosphere to provide the oxygen the roots need, and enough water to provide both the water and the nutrients that the plants need. So oxygen, water, nutrients. And if you have enough water and air within your soil, you're also keeping the microbes happy. So there are microbes, bacteria and fungi, that can live in saturated, oxygen-free soils, in wetland soils, if you will, swamp soils. But generally, most of the microscopic microbes within the soil, like an oxygenated, rich environment, but a moist environment. So not saturated, but damp, moist, damp, and enough atmospheric oxygen to keep them going. So if you have a soil, again, that's 50% solid, 25% gas, 25% water, chances are you're giving the microbes what they need as well. And if the microbes are happy, they're going to be decomposing a lot of organic matter and releasing a lot of nutrients for themselves and for the plants. So how do we get this balance of 50% solids, 25% water, and 25% air or gas? Well, this balance relies on another important physical characteristic of the soil. So we talked about soil texture, which is the percentage of sand, silt, and clay. The other physical characteristic that's really important for soil health is soil structure. And that refers to basically how the soil clumps. So to put it a little fancier, how the soil solids are arranged together spatially, but really it's clumping. How does the soil clump together? It doesn't seem like clumping would be that important, but it really is. So if we were to look at a column of soil in the field, natural soil, from a distance, it looks solid. But once you get up close to it, you'll see that it's actually composed of these little discrete clumps called PEDs, P-E-D-S, like short for pedestrian. A PED is basically a visible clump of soil that we can see with our own eyes. And again, it doesn't seem like these clumps would be all that important, these PEDs, but they really are. Here's some of those PEDs in real life. So oftentimes, up at the top of the soil, in the topsoil, we find small little PEDs. We call that granular structure. So we get a little deeper into the soil, we get into some of our clay bands, and we have blocky structure, which is basically the same shape as granular structure, but each PED is just a little bit bigger than those granules. So the shape doesn't change too much, but the size gets bigger. And that's what we're seeing in that little illustration to the right. Granular structure on top, blocky structure down below. Fortunately, in urban areas, we have a lot of this stuff, which is called platy structure. which often is what forms when you take a nice, well-formed granule or block and you squish it under a weight, like the track of a backhoe or a bulldozer, or just a lot of foot traffic. Or if you're in an agricultural area, you can get compaction from the plow that's used to plow up the field, or from extensive hoofed animals walking on the surface like horses or cows. So platy structure is often a sign of compaction. And these last two ones, massive and single grain, those are basically a lack of structure. Those would be structureless soils, but they're sort of structureless in the opposite way. So a massive soil is a soil that's just one huge block all adhered together. Whereas a single grain soil is a soil where nothing sticks together. Everything is just a little loose individual grain. So basically think of dust. If you pick up a handful of dust and the wind blows it, you'll see that it scatters all the little individual particles of sand, silt, and clay. And that's what single grain is like. And basically there's nothing in that soil to cause it to adhere. Whereas a massive soil is just one huge, massive chunk. How is soil structure created? Well, basically, what we would consider to be a good soil structure is a soil that has beds that are fairly solidly formed. They adhere to themselves fairly well. They don't dissolve when water passes through. They don't dissolve when a little bit of weight is put on top of the soil. But between each bed and its neighboring bed, there's an open channel, a pore, that separates those two neighboring beds. In order to get this sequence of beds surrounded by pores, you need two things. You need binding agents and you need burrowing agents. Binding agents are those natural things in the soil that cause clumping, cause aggregation, cause things to stick together. What are some of those aggregating materials or binding agents? Clay is a very good one. We all know how sticky clay is. Organic matter is a very good binding agent too. Now, a leaf falls on the forest floor, that's not going to cause anything to stick together. But as that leaf decomposes into what we call soil humus, humus being a highly decomposed organic matter, that highly decomposed humus is very sticky and is a very good aggregator or binder of other soil solids. The decomposition of materials via microbes tends to create these sort of sticky byproducts. Some people call them mucilages, which you can kind of tell from the base what these things feel like. Those are really good soil binding agents. And then the root hairs of both plants and fungi are very good binding agents as well too. These roots, they kind of act like twine in a way that cause a little microped, if you will, to, be intertwined with a neighboring microped and almost kind of ties things up into a bow, for lack of a better term. Now, if all we had was binding agents, all our soil would be massive because everything would just stick together. But we don't. We have these pore spaces as well. So in addition to the binding agents, we need burrowing agents to create those pores, to create that separation from one bed to its neighboring beds. So what are some of these burrowing agents? Well, the one you might think of first is worms, and that's a great burrowing agent. They're basically a living, breathing, tunneling organism. Everywhere they go, they're leaving a little worm channel or worm channel behind them, and that is a great way, great pore space for the soil and helps to differentiate neighboring beds from each other. Roots are great burrowing agents as well. There's other burrowing organisms within the soil, insects, some of the larger animals like the fox or the groundhog, those are burrowing agents too, moles, but insects in particular are very good burrowers. And then we have just the purely physical, non-biological ways in which pores are created: wetting, drying cycles, shrinking, swelling cycles, and freeze-thaw cycles. All of these cycles cause the soil to expand a bit in volume. When it's wet, it expands. When it's dry, it shrinks back. Shrinking, swelling is specifically referring to clay. There are some types of clay that shrink significantly when they're hydrated, when they're wet, and swell significantly when they're hydrated or wet, and shrink significantly when they get dry. And then freeze thaw. If you've ever had, well, I won't say this, but basically ice is actually a little less dense than water, which is why your ice cubes float in your drink. When water freezes, it expands a bit in its volume. And when it melts, it shrinks a bit in its volume. All of these processes, wetting, drying, shrinking, swelling, freeze thaw, basically change the volume of soil in these yearly cycles. And as that volume changes, eventually, as the soil swells and shrinks over many, many seasons, what's left behind are nice, fairly consistent pore spaces. So we've got our binding agents to cause everything to stick together. We've got our burrowing agents to work their way through the soil and allow for pore spaces to form between those well-adhered soil beds. And what we have left with is, again, a soil that has about 50% solid material. And then the burrowing agents and the pores that they create allow for 25% by volume water and 25% by volume air to inhabit the soil. It's those pore spaces that allow the air and water from the surface to get down, percolate down into the soil, and stay there. Hope that makes some sense. Basically, a well-structured soil will look kind of like a bowl of cereal. What happens in that bowl of cereal when you pour water on top? Does the water stay on top? No, percolates down quite quickly between your Cheerios or your grape nuts or your cornflakes, and gets down into that bowl of cereal instead of just sitting up on the top. And that's what should happen when water, rainfall or snow or sleet falls on a well-structured soil. It should absorb down into the soil fairly quickly. And while we can't see it during dry periods, oxygen is absorbing down into that soil fairly quickly as well. So we talked about what soil is made of. We talked about some of the important physical characteristics of soil, the soil's texture, the soil's structure. How does soil form? What are the natural processes that take, in our case, in this area, usually solid bedrock, and break it down and turn it into these well-structured assemblages of sand, silt, clay, organic matter, and pore spaces that are full of oxygen and water? Well, there are 5 natural forces that we call the 5 soil-forming factors or soil-forming processes. Usually it's called the 5 soil-forming factors. I should change the slide to say that. And the 5 soil-forming factors go by this relatively inelegant acronym, CLORPT. I think if you sound it out, it sounds to me almost exactly like the sound of a pebble or a rock being thrown into the middle of a pond. CLORP. But if you can remember that acronym, it makes for a very good mnemonic device, and hopefully it'll help you remember the 5 soil-forming factors. So in that way, it's a good acronym. If it helps you remember, it's a good acronym, even though it doesn't exactly roll off the tongue. One thing you'll notice is there's 5 soil-forming factors, but there's 6 letters in CLORPT, and that's because the first 2 letters, CL, stand for climate. Climate, basically, if we're going to break it down to its simplest parts, it's the combo of temperature and precipitation in an area. And the general rule that we see with soil is that the hotter the climate is and the more rainfall there is, the quicker things decompose, the quicker things break down, both organic matter and that solid rock. Put a big chunk of what seems like eternal granite out into a hot and wet environment. Over time, that granite is going to break down. Geologic span fairly quickly too. By the human span, still a very slow, long process. But that granite will break down into sand and then eventually silt and clay. Just give it enough time. And in a hotter and wetter climate, that time is much shorter. Organisms, the things that live in and on the soil, are the next soil-forming factor. This is not the only thing they do, but one of the important things that organisms do in the formation of soil is they break down, but they both add organic matter and break down organic matter. So if all the leaves and twigs and animal manure and carcasses that landed on the soil surface throughout the year did not break down, we would basically be buried in waste up to our necks. But luckily, all those bacteria and fungi and other critters that live in the soil, but bacteria and fungi in particular, see that fallen material, that dead material, as their food source, and they start to decompose it. And as they decompose it, they break down the volume of that dead organic material, the twigs, the branches, the manures and such, and they turn it into soil humus and also carbon dioxide, which goes back into the atmosphere. And as they break it down, they also release the nutrients that are stored within that organic matter. And some of those nutrients go out into the soil or dissolved in the water, and they can be taken up by the plants. So that's how nutrients kind of cycle through, and that's how we deal with all the organic waste that gets naturally produced throughout the world. Otherwise, again, we'd just be buried in it. We've got relief, third soil forming factor. Relief is just another word for your topography, your landscape position. Relief has a big amount of control over the erosion and deposition that occurs within a soil, and it's fairly intuitive. The steeper the slope you're on, the more natural erosion there's going to be. Even if you have a really nice cover of prairie plants, of grass, or of trees, which will help prevent erosion. But even then, if the soil is steep enough, you're going to get much more erosion occurring on steeper soils than on flatter soils. And the nice thing about eroded material, and all material for that matter, is it only ever travels in one direction, and that's downhill. So stuff that erodes off those steep slopes flows downhill and deposits in the valleys or flatlands down at the bottom. So relief really determines the balance of erosion and deposition in your soil. And the general rule is the flatter things are, the more deposition you have, the more sloped things are, the more erosion you have. And you particularly have more deposition when you're at the base, the flat base of a steep slope. Fourth soil forming factor is parent material. So if you think about us, we get our traits, our physical traits from our parents. Soil gets a lot of its physical traits from its parent material, which is the rock or sediment from which the soil weathers, from which it forms. So I was saying most of our parent material around here in Northern Virginia is bedrock. But if you happen to live in southern or eastern Arlington, or really any part of Alexandria, the parent material of the soils there is actually water deposited bands of sediment. So sediment came washing in with sort of our ancestral Potomac River, and in a few cases, depending on where you live, the Atlantic Ocean, and deposited there. So the silt, sands, and clays washing in from those waters and then depositing out in these old ancient floodplains, which all of Alexandria was, and a lot of Arlington was as well too. That becomes the parent material for those soils. So that parent material in eastern Arlington, southern eastern Arlington, and all of Alexandria is water deposited sediment. Whereas if you go to the west, basically any spot west of I-95 in I-395 is the parent material is mostly bedrock at that point. So those highways are a fairly good divider between those two major parent material types. And then finally we have T, time, our fifth variable, and kind of a master variable as well too. It takes a lot of time to create soil. It's a slow process. It's estimated that it takes 100 to 500 years to create every new inch of soil. And if we look out at the soils around us, we're looking at oftentimes 2 to 4 feet of highly weathered soil. So that means that stuff has been sitting and weathering in place for potentially 30, 40, 50,000 years in some cases. That's not, some people despair a little bit when they hear that. It can take up to 500 years to create an inch of soil. That fact is not to say that if you have bad soil in your backyard or your front yard, it's going to take you 500 years to improve it. It may take you 500 years to create a new inch of depth of soil, but that's not what you're trying to do as a tree steward, as a gardener, as a landscaper. What you're trying to do is take the depth that you already have and make that more fertile. And that can be done within a growing season or two. So don't let that slow soil formation despair you from thinking you can't get better soil. You definitely can, and within a relatively quick period of time. So the 5 soil forming factors, clorpt, climate, organism, relief, parent material, and time, manifest in different ways in different areas. Generally, if we're talking about soil changes over smaller areas like Arlington and Alexandria, we're talking about changes in relief and parent material and time. If we're talking about changes in soil in Virginia versus California versus Alaska, we're talking about changes in climate. Climate kind of creates big changes over big areas. Parent material creates big changes over medium-sized areas, and relief can create big changes over very small areas. So if the soil in your neighbor's yard is different from the soil in your yard, it's probably an issue of relief. If the soil on the other side of the county is different from the soil in your yard, that could be a combo of relief and parent material. If the soil in another state is different from yours, we might be looking at the influence of climate. And of course, all the 5 soil forming factors interact with each other as well too. Obviously, if you have different climate, you're going to have different organisms living on and in the soil. So keep that in mind as well too. But it's those 5 soil forming factors and the way they interact with the soil on the ground and interact with each other that creates the high amount of variability and variety we see in our soils. It's estimated there's about 15,000 unique soil types within the United States, and it's thanks to the differing application of the 5 soil forming factors over different areas. Now, soil is variable in one spot as well too. So if you stand perfectly still and dig from the surface down to a depth of 3, 4, 5, 6 feet, you're going to see a lot of changes as you go from the top of that soil to the bottom. That has nothing to do necessarily with the 5 soil forming factors. It's just the way soil forms is it tends to, over time, given enough time, it will form into these layers called horizons. So soil is kind of like a layer cake. You get different highly variable layers as you go from the top to the bottom. These are all the possible layers that you could find in a soil, and we call these layers horizons. That's not to mean that you're going to find these layers, all of these layers in your soil. You might only find a fraction of them. You might, in some soils, you might only find 2. But I wanted to go through all the ones you could possibly see in your soil. So don't think that you'll necessarily see all of these. But oftentimes what you do have, if you've got anything growing on your soil, you will typically find a little bit of an O horizon. Most people don't even think of this as soil because it's above the surface, but O stands for organic, and the O horizon refers to a loose litter of organics on the surface of the ground. So that fresh leaf that fell yesterday, that's not O horizon yet. To be considered the O horizon, that organic matter has to start to decompose. So as you go out into the forest and you brush aside that first top dry, crispy layer of leaves, you'll find underneath that the layers of organic material below that, which still are mostly leaves, start getting a little bit darker, a little bit more moist, and they start breaking up into smaller and smaller pieces. They're basically being shredded. That's the O horizon, that beginning decomposition of organic matter, organic litter right on the surface. As the O horizon decomposes further, it creates soil humus, which is, again, that highly decomposed organic material. Basically, if you have a compost pile in your backyard, you're creating soil humus. Finished compost is basically soil humus. That soil humus from the O horizon gets incorporated, gets washed down into our first subsurface layer, which is called the A horizon. And this is where usually people think of soil as starting. The A horizon, in common parlance, is our topsoil. And it's usually fairly easy to see where the A horizon stops, because you generally get a very big change in soil color, because the A horizon has that nice dark cocoa brown or black type color. And the reason it has that color is because it's full of soil humus, which is itself very dark brown or black. The A horizon in our soils around here, even healthy ones, is usually no more than 5 inches thick. Now, if you have a garden where you've been adding lots and lots of organic matter over the years, your A horizon might be thicker. So just because we don't have thick A horizons in Virginia, it doesn't mean our soil isn't healthy. That's just naturally how our soil forms in the climate that we have around here. If you go out to Iowa or Illinois or some of the other Midwestern states, the real breadbasket farming states, those used to be prairie, and prairie, especially Midwestern prairie, tends to create a very deep A horizon. So it's not too unusual to get 18 inches of A horizon in a Western Iowa or Western Illinois soil. But around here, I'd say you're pretty lucky if you get 2 to 4 inches. And despite that narrow band, that narrow depth of the A horizon, it is an extremely important layer because it's the biological powerhouse of the soil. So that humus and other associated organic matter, as it's decomposing within the A horizon, it's releasing nutrients. Humus does a really good job at absorbing water as well too. So the A horizon tends to have a lot of nutrients, a lot of moisture, and as a result, you find a lot of microbes, bacteria and fungi, and a lot of small plant roots living within this A horizon because they're after those nutrients and that water as well too. So a very narrow layer, but a very biologically powerful and rich layer. Below the A horizon, you might, I'd say less than 50% of the time, but you might find what's called an E horizon. And I think of the E as standing for exit. It's the layer that things have washed out of. It's what we call leached. And leached means a material that has a lot of the colorful and dissolvable materials washed away. And the reason the E horizon is so leached is because as the A horizon is forming and organic matter is breaking down in it, that breakdown tends to create a lot of organic acids. And those organic acids get washed down through the soil every time it rains or snow melts, and it passes through the E horizon, and it kind of acid etches or acid washes the E horizon out and dissolves a lot of materials in the E horizon and takes them further down into the soil where they can be deposited. So the E horizon has had a lot of things stripped or leached out of it, and as a result, it's kind of a pale color. The texture may not be so different. It's not necessarily that it has less clay than some of the other layers, although sometimes it does. But what you're looking at in the E horizon is basically naked minerals. So we think of our soils as being kind of brown or red, yellow, or orange in some cases, but oftentimes those colors are just coatings on the sand, silt, and clay. It's not the color of the sand, silt, and clay itself. If you leach off all those coatings, what's left behind is kind of a pale gray color. That's what the natural uncoated color of sands, most sands, silts, and clays are. So again, the E horizon is like the acid washed jeans layer of the soil. It's the layer where a lot of things have just washed out, leached out, and been stripped out and deposited deeper in the soil. And again, if you do see an E horizon in your soil, it's probably not going to be as dramatic as this one. It'll be, kind of almost think of an A horizon that's been put through the wash cycle too many times, and that nice dark color is kind of bled away. It also tends to be fairly thin, just like the A horizon. So if you have a 2, 3, or 4 inch E horizon, it's unusual to get one that's much thicker than that. So I like this picture because it really shows the layers well, but the depths here don't match up very well with the common depths of layers that we find in Virginia soils. That extends to the next layer, the B horizon. So I'd say for most of you, if you're digging in your backyard, you probably go straight from the A to the B. The B horizon has our 2 C's, color and clay. So a lot of the material that gets stripped out of the E horizon gets deposited in the B horizon. Those fine particles of clay that might have been in the E horizon, they're getting washed out over time, deposited in the B horizon. All that colorful soil that you see, the reds, oranges, and yellows, that's B horizon stuff. What is that color? Reds, orange, and yellows are types of iron oxide within the soil. Iron in the soil combining with oxygen dissolved in the water that's passing through. That iron oxide, again, often forms higher up in the E horizon, but over time it gets stripped out and deposited down into the B horizon. And over time, as the soil gets older, the B horizon will actually get thicker as clay and iron oxides get deposited deeper and deeper in the soil. So if you have what's colloquially called red Virginia clay, really what you're talking about is your B horizon material. So if your soil is very red or rusty orange or even kind of a orangey brown or yellowish brown, you're probably in your B horizon. And especially if that material gets really hard and dense and almost brick-like during the summer when everything is hot and dry, chances are you're in your B horizon, because that's where we find the most clay and the most color. Below the B horizon is our C horizon. And this is where basically the highly weathered soil begins to peter out and the just beginning to form layers of soil start kicking in. It's kind of a border layer between the highly weathered soil above, highly horizonated soil above, and the solid, unweathered material below, which can either be solid rock or unweathered sediment that was deposited by wind or water. Typically, in our C horizons around here, we start to see a decrease in clay. So if you're digging down real deep in your soil and you start feeling as if the soil is getting drier, looser, more powdery, more dusty, or oftentimes more gritty and more full of larger gravels and rock pieces, chances are you're exiting your B horizon, getting into your C horizon. This is where the clay usually drops out and the soil gets drier, grittier, and dustier. And then if you dig down deep enough, you will eventually hit the R horizon, which is solid bedrock. If you happen to live in, let's say, Old Town Alexandria, you might have to dig down 300 feet before you hit bedrock. If you happen to live in Western Fairfax and Chantilly or Dulles area, or Eastern Loudoun County, or Manassas, you dig down 2 feet and you're likely to hit bedrock. So there's a real wide range in the depth of bedrock. But if you dig down deep enough anywhere in the world, you will eventually hit that solid rock. So those are all the possible layers we can find in soil. And again, that's not to say that you're going to find all of those in your soil. That's just the maximum number of layers you could potentially find. So now we know a little bit about soil formation, the 5 soil forming factors, the layers that soil naturally arranges itself into. What does a healthy soil and plant ecosystem look like? Well, I would say a healthy soil would have a nice A horizon with lots of organic matter and that good granular structure. Granular structure tends to make the soil very loose. We call it kind of a crumb structure. You can almost just stick your fingers through it and have those little granules fall between the cracks in your fingers. It's very loose. It's not very dense. It's very easy to work up. Lots of organic matter means there's lots of organic carbon for our microbes to break down. And as they're breaking it down, they're giving themselves energy and nutrients, but they're also releasing nutrients into the soil, some of it being able to dissolve into the soil water. So they're both enriching themselves and enriching the soil, which is good for the plants. That nice granular structure has, again, solidly adhered PEDs, but big pore spaces between those PEDs, which allow air and water from the surface to easily get down into the soil to provide these critters the oxygen and the moisture that they typically desire. And that oxygen and moisture also is what the plant roots typically desire. Yep, got ahead of myself. Good crumb structure allows in plenty of oxygen and water. Of course, as water passes through the soil, it dissolves the nutrients that those microbes released as they broke down the organic matter. And once those nutrients are dissolved, then they are available for uptake by the plants, because the plant roots, remember, only take up 2 things from soil: oxygen and water. So if they want their nutrients, those nutrients have to be dissolved in water. To get those nutrients dissolved, for the most part, they have to be worked over by the soil microbes first. And it's a virtuous cycle, because now that there's a lot of nutrients getting into the roots, the plants are healthier. They're putting on more mass because they're well fed. And a well-fed plant grows big and strong, grows new organic matter, and transfers a lot of that organic matter back into the soil through leaf fall, through twigs that fall down during heavy windstorms. And often, I shouldn't say often, all the time, plants also exude organic matter directly through their roots as a way of sort of goosing the microbial population down there to help the microbes, which then help the plants by breaking down organic matter and releasing those nutrients. So healthier plants add more organic matter back to the soil, and this strengthens the cycle. As we get a little bit deeper, a healthy soil plant system will have a B horizon with a good amount of clay. Oftentimes we think of clay as a bad thing, and it can be a pain, especially if you're trying to dig in the middle of summer and it's really dry and that clay is dried up like a brick. You're probably not going to be having a good time, and you'll be shaking your fist at that darn red Virginia clay. But red Virginia clay does a lot of good things for us. That clay is very good at retaining water. So it retains a significant amount of water for uptake by some of the deeper roots. In addition, while it's not nearly the biological powerhouse that the A horizon is, there is still quite a good and healthy and robust microbial population down in the B horizon. And there's enough organic matter that gets washed down from some of the top layers and deposits in the B horizon for it to provide a good amount of nutrients to our plant roots as well too. So it absorbs water, some of the deeper water, which allows the plants to drink, especially during droughty periods. And it does still release nutrients, not to the level of the A horizon, but still to a significant level. And then we'll also find it's very good for water quality as well too, because the B horizon is very good at absorbing materials that were leached out of the top. Dissolved materials that get leached out of the A and the E horizon will often deposit in the B horizon instead of just flowing down all the way to the groundwater, where we don't want lots and lots of nutrients to be. The C horizon has generally, the deeper we go, the less function those layers have, the less benefit they provide towards soil health and plant health. But that's not to say that they're not important. So the sea horizon generally is fairly sandy, fairly gritty, fairly dry compared to the materials above the B, the E, the A. But there's still water retention that occurs there, and that water is accessible by some of the deepest roots. So again, if you've got a nice taproot from your plant, it can drink some of that deep water, and that can be very helpful during the hottest and hottest and driest parts of the year. And the sea horizon also, like the B horizon, helps to filter out soluble material. It has less clay, so it's not as good as filtering, but it still does provide some filtering, which is important because, again, as that groundwater percolates deeper and deeper and deeper, the groundwater that eventually flows into our deep aquifers, our more permanent aquifers, and into our streams and rivers, we want it to be fully filtered, nice and clean, and not full of nutrients that we prefer to have stay in the soil. And anything that passes through the sea horizon gets down into some of our deeper groundwater and groundwater recharge. So if you've ever wondered why streams flow even when it's not raining, it's because there's groundwater leaching through their banks, leaking through the banks of the streams. And it's this groundwater that passes through the deepest layers of the soil that really help to provide that consistent recharge of our local streams and rivers to allow them to flow even when it's been dry for weeks or potentially months. Now, with this healthy soil ecosystem, what happens when we develop that land? Well, development causes a lot of changes in soils. Fortunately, they're pretty much all bad. So the first one that we may be all familiar with is compaction. So this is what happens when we take that nice, loose, well-structured soil that has these nice, well-adhered together soil beds with big pore spaces opening up between them, which allows the soil to have 25% by volume water, 25% by volume air. What happens to that soil when we run a bulldozer over it or some other heavy construction machinery? Well, it tends to pack that soil down and squeeze out a lot of those pores. So what was once the healthy dispersion of solids, gases, and waters now becomes a much more heavily solid material because those pore spaces are squeezed out. There's less available volume for the soil air and the soil water to inhabit. So your compacted urban soils are going to have a much higher percentage of solids by volume than your natural uncompacted soils because of that loss of pore spaces. When you lose pore spaces, you reduce the ability of air and water to pass or infiltrate from the surface down into the soil, into the rooting zone. So I call a compacted soil impervious light. You might have heard of the term impervious surface before. An impervious surface is something like a rooftop, a concrete, asphalt paving, any usually human-made surface that does not let water pass through. A compacted urban soil is not fully impervious, but it takes in a lot less water and a lot less oxygen than its natural foremothers would, its uncompacted soil would. So here's your well-structured soil, your nice loose soil out in a forest or in a field or even in a well-maintained yard. It rains, that soil has that good structural beds that are fairly solidly adhered together. They don't dissolve and break apart when they're wet, but they have these big pore spaces between them and their neighboring beds, and those pore spaces are like highways that allow water to quickly pass down through the soil during a rainstorm. So a well-structured soil is an absorptive soil. It's like a sponge. We take that same soil and squish it under a heavy weight. It becomes compacted. It becomes platy. Those soil pads are squeezed together, and a lot of those pore spaces are squeezed out, and what pore spaces are left tend to be smaller. Same rainfall hits this compacted, platy soil, and a lot of that water never gets a chance to get into the soil, and instead it either pools or flows off the surface as stormwater runoff, and a smaller fraction infiltrates down into the rooting zone. So again, this is why I call it impervious light. It's not a totally impervious cap on the soil, but compacted soil prevents a lot of water from entering. Compaction also creates a strong soil, a dense soil that is just all around harder. And sometimes that soil can be so hard that the plant roots don't have the energy or the force to push through, to penetrate. So this is a fairly typical scene you see to the right here. Oops. That is, a street tree. Looks like maybe a willow oak or something like that, in what I assume is a fairly new subdivision. What would be interesting is to see trees like this after 15 or 20 years. If this were good soil, this would be a really good growing medium for that tree. It's got tons of sunlight, so it can make plenty of photosynthesis. If it gets enough rainfall on the mulch and the grass there, it should have enough water, and it's not competing with other big trees that might shade it out. So a tree like this should be able to grow fairly quickly. But I have a feeling if you come back in 20 years, this tree is going to look much bigger. And I think the big reason for it is that soil around it on all sides, but especially the soil underneath the sidewalk and underneath the roadway, is highly compacted. And the roots of that tree just may not have the strength, the force to be able to push through that compacted soil. So in effect, those roots may just be constrained to that little area of mulch that you see right there. And if the roots are constrained and can't grow out wide into the soil, the plant is going to be stunted. The roots basically determine how big that tree can be in the end. So a smaller root system means a smaller tree system. And I think this is a very good illustration of that. This is one of our most famous roadways. This is Pennsylvania Avenue between the White House and the Capitol. And these are all willow oaks that you see. And you can see they're all planted at basically the same time. So they're the same species and same age of trees. But if you look at these trees on the left side of the tree, of the street, of the sidewalk, I should say, versus the trees on the right side, there's a big difference in how well they're doing. These trees on the left are kind of spindly and stunted. Trees on the right are much bigger and have a much fuller canopy. And the reason for this is because these trees on the right, while not a perfect growing medium, they have access to all this soil, this 30 to 40 feet of soil between the sidewalk and the front of this building behind it. These trees over here are kind of put into a little bit of a tree pit, or as we call them sometimes tree coffins, and they're surrounded by soil, but that's the soil that's underneath the roadway and the soil that's underneath this very wide sidewalk, and that soil is going to be very dense and very compacted, probably to such a degree that these roots really have a hard time penetrating through it. So those roots are kind of constrained within this little tree box, and that's all they really have easy access to. And as a result, the roots are stunted. They can't force their way out of this predicament that they're in, and the tree is stunted as well too. And just as a bit more of a local example, we were contracted a couple of years ago to do a study for Arlington County to look at the quality of lawn soil in new versus old residences. And by new residents, we mean ones that were usually either just built or about to be finished building. They still, in some cases, were constructing them, but they had not yet been sold to the first owner. So they were still under permit. So these are basically brand new houses. And the old residences were a collection of homes from the 50s and 60s. So average age was about 65 years old for the old residences. What we did is we took density measurements of the lawn soil in front and back for 10 of each type of house. And what we found is that the average density was about 1.37 grams per cubic centimeter for the new houses and 1.15 grams per cubic centimeter for the old houses. So that's about a 20% increase in density for the new houses. And that doesn't sound like a huge amount, but it's something, that's for sure. It was very consistent as well too. But where we really saw a big change was in the infiltration rate. And this is, again, the rate at which water can soak down into the soil. And the way we test this is pretty simple. We get these two rings of sheet metal, and we kind of pound them into the ground so they look like a bullseye that's lodged itself into the ground. And then we fill those rings up with water, and we measure how quickly the water in that central ring disappears, how quickly it drops. What we found is for the new residences, it dropped at a rate of 0.13 inches per hour. So just basically slightly over 1/10 of an inch per hour. And for the old residents, it was 1.28 inches per hour. So there was about a 90% reduction in the speed at which water infiltrates or percolates down into the soil between the old houses and the new houses. And this can be a real issue, both for the health of anything that's living in there, because I mean, 0.13 inches per hour, unless you have a really flat property, most of that water that falls on is just going to become surface runoff. It doesn't have the residence time to sit on that lawn and percolate down into the soil if it's only passing through at 0.13 inches per hour. Whereas for the older residences, even though 1.28 inches per hour isn't a record-breaking infiltration rate by any means, chances are for most of your rainfalls, that old soil, that old lawn soil, is going to be able to absorb it and create very little surface runoff. So the reason that the county wanted us to look at this is because their existing stormwater regulations, in fact, the state's stormwater regulations, are based on impervious surfaces. So if you build a big new house, you add more rooftop, you add more driveway, you have to then by law control the volume of stormwater that flows off those impervious roofs and driveways. You do not have to control the water that rolls off of your lawn, because it was assumed, well, it was lawn before and it's lawn now, it's going to behave fairly much the same. But our study showed that that was not the case. The construction inherent in building this new big house compacted the soil significantly, and that greatly reduced the infiltration rate. So for these new houses, new runoff is not only coming from the roof and from the lawn, but also from this highly compacted, barely pervious soil in the front and backyard. And this can cause big issues for the neighbors. So let's say this house is sloped downhill. Well, it's great that the new house is controlling the runoff off the roof and driveway, but now you've got this big lawn that's not really absorbing much water and instead is shedding lots of runoff onto the neighboring property. So I think that's one of the reasons that we see a lot of flooding complaints in these neighborhoods that are going through what we call infill redevelopment, where basically the old houses are getting knocked down and bigger ones are being built up. So anyway, long story short is the way the Arlington County solved this is that they now require soil remediation on these new properties. Basically, the developer has to go in, till and compost to the soil after the house is built before the sod is put down, to try and recreate that looser, fluffier, more absorptive soil that existed before the site was constructed upon.
Excuse me, Dan.
Yes.
There's a question in the chat. I should have asked you, do you want to wait to answer questions or?
No, we can do it now.
Okay. I'll read it to you.
Sure.
I've heard that sod, especially because it is often laid on compacted soil, is largely impervious. Are there measures of imperviousness, and would you know what the measure for sod would be?
Well, you're pretty much looking at it with this slide. So you can tell this is an example photo. We obviously looked at more properties than just these two, but that house to the right was one of the new properties. And most of the new houses we looked at were similar to this. They had a very lush green looking lawn, and that's because sod was laid down. And what we found is basically that sod had, maybe a half inch of root mass below it and some nice dark organic soil, A horizon, but that A horizon was brought in with the sod itself. That was basically the organic matter that was clinging to the roots of the sod when that sod was cut from the sod farm in Western Maryland or Southern Virginia or wherever it came from. Below that was basically local compacted soil. So yes, what we've found is you can grow sod, a nice green, healthy looking sod lawn, on really compacted, not so healthy soil. And that soil will not absorb a lot of runoff, even if the sod looks nice and green on the surface. That's not to say that all sodded surfaces are in bad shape. You can put sod down on top of healthy soil and it's going to look perfectly fine too. But what we're finding is this sod is a very good way to cover up unhealthy soil. It still looks nice and green. People are none the wiser because you look at it from the surface and it looks like it's performing well. But like the question states, no, we don't see in many cases good infiltration on sod because of the compactedness of the soil below it. Good question.
I wrote the question before you showed this slide. So.
Gotcha.
Perfect.
Yep. Good illustration of it. All right, so back to the slides, some more urban effects. We get mixing of the soil as well too. And this is one thing that we saw very clearly at these new residences. There really wasn't much of an A horizon left, a topsoil left. It basically, again, had just a little bit of organic matter little bit of A horizon that was basically brought in with the sod, and then we had this kind of mixed up subsoil down below. Because when you build upon a soil, it's inevitable that the soil layers are going to be partially mixed together. So you basically take all these segregated layers, A horizon, E horizon, B horizon, C horizon, and you kind of homogenize them all, mix them all together, and then pack them back down. This breakup of the soil, this mixing of the soil, causes the destruction and death of a lot of the fungi, because remember, the fungi usually exist in soil as these long, thin, delicate root hairs. So every time you're mixing the soil, or putting a bucket of a backhoe down into the soil, you're basically cutting through thousands and thousands of fungal root hairs, and this kills them off. And it also causes that topsoil, which again around here is only about 2 to 4 inches deep, right at the surface of the soil, to be mixed and dispersed throughout the entire depth of the soil. So this is a little bit of an exaggeration, but again, the soil kind of gets homogenized afterwards, and it really is harmful to have that loss of productive topsoil, to have that topsoil kind of evenly mixed in throughout the depth of the soil, because you really need to concentrate those microbes and bacteria and fungi and soil humus up at the surface to create a healthy A horizon, a healthy topsoil layer. If it gets mixed throughout the soil, it's still there, but it's not going to be a functioning topsoil layer anymore. Loss of productive topsoil causes a loss of microbes, a loss of soil humus, and probably most importantly, a real loss of nutrient cycling. This really puts a kink in the natural nutrient cycle that we see in soil. Some other changes you might see are pH changes. Sometimes this is very localized and due to local land use, especially if you're using concrete walkways and roadways. Concrete has a little bit of limestone in it. Our soils around here are naturally a little bit acidic. So you put that limestone-rich concrete on top of the soil, it can often cause the soil pH to rise within a 2 or 3 foot buffer around that concrete paving. On the other hand, there are certain fertilizers that can lower pH, especially those that contain ammonium or sulfur. Now, adding fertilizer one time probably won't make a huge change, but if you're adding a little bit of fertilizer every spring or so to a garden plot, especially with a fertilizer that contains, again, ammonium or sulfur, you'll probably see your pH of your soil begin to slowly decrease over the years, become more acidic. And pH is a really important characteristic of soil. Not because, I think this, certainly when I was a kid, I thought this, but you think acid is bad. You see too many cartoons where people drop something in acid and it dissolves. Acid is not bad. And again, our soils around here are naturally acidic. So an acid soil isn't eating away roots. It's not dissolving microbes or anything like that. Really, what's important about pH in soil is that certain ranges of pH make certain nutrients more or less available. And generally, a soil will grow in a pH at which the available nutrients are to its liking. And most of our local plants around here enjoy a pH between about 5.5 and 6.8. A little outside that range is going to hurt them too much, but that's kind of the sweet spot right there, 5.5 to 6.8. You can see from this illustration, those two bars are kind of bordering that 5.5 to 6.8 sweet spot. And we see all these horizontal bars that represent the relative availability of our most important nutrients: nitrogen, phosphorus, potassium, calcium, magnesium, and such. The wider the bar gets, it means the more of that nutrient is available. And by available, it means available to dissolve in the water and therefore be taken up by the plant roots as they suck up water from the soil. The thinner the bar gets, the less available that nutrient is. So we look at something like phosphorus right here, one of our most important nutrients. As we drop down below pH 5.5, phosphorus gets very unavailable because this bar gets very, very narrow. There's also a little weird spot here where phosphorus gets unavailable at very high pH, but this is about pH 8.5, and frankly, we're almost really never going to see that in our local soils. That's way too basic. But the reason that this 5.5 to 6.8 range kind of represents a sweet spot is that most of the stuff that critters need is available in enough of a soluble form that they won't see any restrictions. They won't see any stunting as a result of unavailability. There's one here, aluminum, that you see. Aluminum is actually not a soil nutrient. It's good for us, but it's not good for plants. They don't like aluminum. And in fact, if there's a lot of it, it's toxic. So you get too acidic, below pH 5, aluminum becomes quite available, and it can actually cause toxicity for plants. Generally, again, in that 5.5 to 6.8 range, there's some aluminum there, but not so much that it's going to cause a problem for plants. So plants like the pH that they like because it gives them the correct amount of nutrients that they need. And once you get outside of that pH, it means they might start suffering from nutrient deficiency because some of those nutrients that they need are going to start to get locked up in the soil in unavailable forms that cannot dissolve in the water. So that nutrient is there, it's just not available to the plant root. So that's why a change in pH is so damaging, is it changes the availability of nutrients for the worse. And lastly, there's salt. And this one's a kind of obvious one. We put salt down on our roadways and our walkways for safety purposes, of course. But that salt then dissolves in melting snow or rainwater, and a lot of it washes down into our soils. And salt can cause a wilting of plants because basically salt is very attractive to water. So if you put a lot of salt in a soil, the water is going to be more attracted to the salt and be held on the salt very strongly and in such a way that the roots do not have the necessary suction strength to extract that water. The salt holds it more firmly than the roots do in this sort of tug of war, if you will. But salt also has another damaging aspect on soil, is it destroys soil structure. If you put a lot of salt into a soil, it tends to cause the soil beds to basically burst and disintegrate. So if you have that nice structured soil that's got those big pore spaces between the soil beds and allows a lot of water and oxygen to get into the soil, but the worst thing you can do is add salt, because the salt will cause those beds to disintegrate and clog up all of the pores. And therefore, the next time you try and pour water into that soil, it's just going to sit on the top because there's no pore spaces to allow it to percolate down into the rooting zone. And of course, when we have poor soil, we'll also get poor water quality as well too, because soil, as odd as it sounds, is a great filter and sponge for water. Sponge is not so odd, but thinking of soil as a filter is kind of strange, because basically what I'm saying is if you let water pass through dirt, it actually comes out cleaner on the bottom. And there's a variety of reasons for this. It gets into a little bit more complicated chemistry, but the basic premise is that organic matter, specifically soil humus, and clay, have these small little electric charges, positive and negative, that attract dissolved ions. Basic chemistry says that a positive charge attracts a negative charge attracts a positive charge. So these organic matters and clays have these variety of positive and negative charges all sprinkled throughout them, and those help them to attract ions that are dissolved in water and bond temporarily to the surface of that clay and organic matter. And that's very important, because that means as water passes through, stuff that is dissolved within that water comes out of the water and sticks to the surface of the clay and organic matter and is held in the soil. So as the water passes through, it gets cleaner and cleaner and cleaner. And there's all these soil microbes in the soil as well too. Those billions of bacteria, those miles of fungal root hair, they can destroy pathogens. Pathogens are basically just bad microbes, microbes that can cause disease. This is basically how a septic tank works. You put your sewage in a septic tank, the septic tank lets that liquid sewage slowly leach down through the soil. And as it passes through the soil, all the microbes within the soil kill off the bad bacteria that are present in that sewage. And by the time the sewage percolates down to the subsoil, it's been pretty thoroughly cleaned. And water itself is also attracted to clay and organic matter. Water is not an ion, meaning it doesn't have a charge, but it actually has sort of a positively charged end and a negatively charged end. All the charges within a molecule of water balance out and basically come to zero. But the positive charges of water kind of stick on one side of the molecule and the negative charges stick on the other. And that allows enough of a little bit of imbalance that water is also, again, attracted like an ion would be to the surface of clay and organic matter. So as water passes through the soil, a lot of the water itself stays in the soil. Some of it just passes through and is filtered, and that excess water goes down to the groundwater. Some of the water stays in the soil. That's very important too, because we want water in soil, because if it just passed right through, the plant roots would only be able to drink when it's raining. And that's something we don't want. We want to have a lot of that water retained in the soil so the plants can extract that water over the long term between rainstorms. So in the long run, soil filters water and cleans it and retains a good portion of that water volume within the bulk of the soil. So in a way, soil is kind of like a Brita filter for the entire world. The issue is, in urban areas and suburban areas, that soil, again, is getting too dense and compacted. This prevents a lot of the water from passing through the soil where it gets filtered and held, and rather, a much larger portion of that water becomes surface runoff. And when it becomes surface runoff, it runs over the surface, it can pick up anything on the surface, it can erode the surface soil, and it can deposit that material with itself down into our streams and our rivers. And the net effect is that we tend to, with more runoff, get more pollutants down into the rivers because that runoff hasn't been filtered through the soil, hasn't had potential pollutants filtered out of it. And we get just a lot more runoff volume into our streams and rivers. And this causes erosion and scouring out of our stream valleys. So that is my boss, Willie. He's a tall guy. He's about 6'7". And you can see his feet are not touching the bottom of the stream. And his head is not, well, several feet below the top of the bank. So this is probably about a 10-foot tall bank. And this is unfortunately a very common scene for our urban and suburban streams. If you see something like this, these steep, high banks with bare soil, and especially tree roots like this one hanging out into the air, that means that this bank has been, or this stream channel has been incised and eroded out. So just a quick recap. Urban development tends to create a denser soil through compaction. This density reduces the amount of pore space available in the soil, which reduces the amount of oxygen and water that can percolate or infiltrate into the soil and reach the roots and microbes. This lack of percolation increases the amount of water that runs off the surface, which increases erosion. Development creates a strong soil, which may restrict root growth because the roots just don't have the energy to push through. Development disperses and degrades topsoil and humus content and kills off a lot of the fungi within the soil. It can change the soil pH, both higher or lower. And it can cause the soil to be salty as well, too. And all these things are very damaging. So all in all, urbanization typically degrades the fertility, and ecological functioning of soil unless we do something to correct it. So we do nothing to correct the damage. Urbanization is very, very harmful. But there are things that we can do to reverse the negative effects of urbanization on our soils. And that's what we're going to be talking about now, restoring urban soil health. So the new paradigm of plant health is to focus on soil health. Again, soil is the kind of the base of your plants, literally and figuratively. The roots extend through the soil, and if you can get healthy roots, you're going to have a healthy plant. How do you get healthy roots? Got to have healthy soil. How do you get healthy soil? Really, more and more we're seeing it comes down to taking care of the organisms, especially the microbes, the bacteria and the fungi that live in the soil. If we're giving them what they need, if we're giving them good food, if we're making their numbers and their populations large and energetic, they're going to be doing a lot of the hard work of soil management for us. So in a way, we want to focus on soil health to focus on plant health.
The Fairfax County Police Department is actively attempting to locate Justin Lynn, a 12-year-old Asian male with short black hair, possibly wearing long.
Joan, could you can you mute yourself?
Sorry.
Yeah. Thank
That's
you. Dan?
Yes.
We have one question. Does the use of brick instead of concrete for sidewalks help?
It would, in that it wouldn't. I don't think brick would change the pH. And in fact, one of the main constituents of brick is soil, which is why a lot of our red Virginia clay has a brick red color. It's because a lot of red Virginia clay goes into making bricks. So yes, I think that would. Of course, the issue is brick is expensive. It's not as durable as concrete is. But yes, I think from a soil perspective, it would not cause those pH changes that you can see with concrete. However, I would say in the grand scheme of things, the pH changes caused by concrete are bad, but they pale in comparison to the damage we're doing through compaction, through salt additions, things like that. So I don't want to overstate the problem of pH changes, but it is a problem. And yes, brick should be able to help that. Yeah, good question.
Thank you.
So back to this slide, basically what we're beginning to realize now is we got to feed the organisms in order to create healthy soil, which then creates healthy plants. And by feeding the organisms, all organisms are important, but specifically we really do focus on the microbes, the bacteria and the fungi within the soil. So even though they're the smallest, they're by far the largest in number, and oftentimes the largest in mass as well too. So how do we do it? How do we kickstart soil biology? And by kickstarting soil biology, we basically kickstart the soil's food web. Well, not to say that there's, a simple answer to a complex question, but in this case, it is kind of simple. You add organic matter, because what is organic matter except organic carbon-containing material? And that organic carbon is the base of the food web in the soil. That is what the bacteria and the fungi and the other critters in the soil eat as well too. So by adding organic matter to the soil, you are giving food to all the critters living within the soil, helping them to build up their populations and create that healthy nutrient cycle that we really want to kickstart. In addition, organic matter really is good at promoting soil aggregation and structural development. So if you want a healthy structure in your soil, meaning you want that 50% solid material, 25% by volume air, 25% by volume water, adding organic matter is a great way to do it. Because again, organic matter, as it decomposes, it becomes humus, and humus is one of those soil aggregates, those soil glues that causes the soil beds to stick together. And organic matter is also very good at holding water and nutrients. And organic matter is very low density. So adding organic matter to a dense compacted soil will reduce the density, reduce the mass of that soil over time. So I have an illustration to kind of show you the multiple benefits that organic matter has for soil. But, well, I shouldn't say the multiple benefits. This really shows you the benefits that organic matter additions will have for the ability of your soil to hold water. So here we have a bar graph that shows the total volume of water that can be held in soil on the y-axis, and on the x-axis we have our soil texture. So this is like a magical soil where we can kind of twist a knob and change it from a really sandy soil to a really clay soil. So basically what we're doing here is we're starting from 100% sand, and then we're slowly adding finer materials like silts and clays and reducing the sand content until we get up to this soil, which is 100% clay. And then a loam soil is kind of a mix of sand, silt, and clay. So we're going from sandy to clay, sandy on the left, clay on the right. So what happens as we go from that really sandy soil and start adding those fine particles of clay and silt? Well, what we'll find is that the ability of the soil to hold water increases as you get more clay. And that's what we call the soil's field capacity. Basically, if you look outside right now, our soils are at field capacity because of all the rain we've had. Field capacity is basically the maximum volume of water that soil can hold against the pull of gravity. So I use a sponge as an analogy to kind of give you an example of what field capacity is. You go to the supermarket, you buy one of those dry sponges, take it out of its wrapper, take it home, and you put it underneath a dripping faucet. What will happen? Well, for the first 20, 30 seconds or so, all those drips of water from the faucet hit the sponge and absorb into the sponge. And then after about 30 seconds, all the pore spaces within that sponge are now full of water, and every new drip of soil from the faucet is compensated for by a drip of water out of the bottom of the sponge and down into the sink. Basically, there's no more space within that sponge to hold any more water. So every new drip of water entering has to be compensated for by a drip exiting. Now you turn off the faucet and you'll see that the sponge will slowly drip for another 5 to 10 seconds, and then it stops. When it stops, that's field capacity. Basically, it means some of that extreme excess water has drained out, but otherwise the sponge is full of water, but that water that's in the sponge is more attracted to the surface of the sponge than it is to the pull of gravity. So gravity's still pulling on it, but the pull of the sponge is stronger and the water stays there. And that's basically field capacity. And field capacity is generally what you have about a day after a heavy soaking rainfall. So some of the biggest pores will have some air in them because gravity pulled water out of those really big pores, but all the other pores are basically full of water, and it's the maximum amount of water that the soil can hold against the pull of gravity, field capacity. And that's usually what we define as the maximum usable content of water within the soil, because the plants can access that water. That's not to say that they can't access a little bit of excess water beyond that, but that excess water beyond field capacity drains through the soil within a day or so. So the plants don't really have long-term access to it. It just drains out by gravity and it's gone. What we'll see as we add more clays, the field capacity increases. And it increases really fast as we go from that 100% sandy soil and start adding those first few percentage points of silt and clay. Then as we get up to a really clayey soil, the field capacity is still increasing, but it really levels out. So we go from 90, 95% clay to 100% clay. Field capacity increases slightly, but very little. Another important water point within the soil is the wilting point. And the wilting point is self-explanatory. That's the amount of water within the soil below which the plant will start to wilt. The thing about clay is that it holds a lot of water, but it's greedy about it. It holds it very, very tightly. Water binds very tightly to clay. So if you have a lot of clay in soil, your field capacity is going to be high, but your wilting point is going to be high as well too, because the clay holds that water so tightly. So here at sand, sand has a wilting point of basically nothing. Any water that is in sand is usually available to the plants because the sand holds that water very loosely. The problem with sand is it just holds very little water in total. As we get up to a loam, our wilting point increases significantly, but then as we really start adding clays and get to that really clayey soil, the wilting point starts taking off much more quickly. And what's important about these two water levels within the soil, field capacity and the wilting point, is that the water that's held, the volume of water held between those 2 points, is the amount of water that's available to plants. So what's important about this illustration is that the area where those two lines are furthest separated is where you have the most plant available water. And generally that's where you have a loam texture, a nice balance of sands, silts, and clays. So a clay holds the most volume of water at maximum, but not very much of it is available to the plant because it's greedy and the clay holds that water too tightly and the roots just don't have the energy to suck that water off that's bound to the surface of that clay. Whereas a loam texture holds less total water, but it makes more of that water available to plants. Sand makes almost all of the water it holds available to plants. It just holds very little water because sand is not very attractive to water retention. So the problem with soil texture is you're pretty much stuck with what you've got. Unless you have the time and wherewithal to hire 30 dump truck loads of good soil to come in and amend your soil texture. If you got a sandy soil, you're pretty much stuck with the sandy soil. And if you got a clayey soil, you're pretty much stuck with that as well too. But regardless of the texture that you're starting off with, if you add organic matter to your soil, you're going to see a real change in the amount of water volume, and especially the plant available water that's held in that soil. And that's because organic matter, especially soil humus, is like clay in that it holds lots of total volume of water, but it's unlike clay in that it holds that water loosely and makes most of it available to the plants. So you add organic matter to a sandy soil, you boost up field capacity significantly, but you just slightly increase the wilting point. You add that same amount of organic matter to a really clayey soil. Again, you boost up the field capacity significantly, but only slightly increase the wilting point because most of the water that binds to the surfaces of organic matter binds softly and can be taken up by plant roots, can be sucked off by plant roots. So you can see basically all of the distance between the bars gets wider, which means there's more plant available water with the organic matter additions, regardless of what the texture of your soil is, whether it's a sand, a loam, or a clay. So this is just one way in which the effect of organic matter is very beneficial to the health of the soil. It really does help the soil hold more water and make more of that water available to the plants. So what's the best way to add organics and to kickstart the soil biology food web in your soil or in your property? Well, I would say the best way is to plant. You just want to have lots of things growing, a lot of variety, a lot of different plants growing for as long as possible throughout the year on the surface of your soil. So a good variety, good diversity of plants and growing throughout a long period of years, a long period or a long proportion of the year, I should say. That's really the best way to get organic matter into your soil and to feed and kickstart the soil biology. And that's because plant roots help hold the soil in place, they help insulate the soil, and they also exude organic matter through the roots. And also, when the plants go into dormancy, they drop their leaves, and that falls on the surface, which also eventually incorporates itself into the soil as organic matter. There are other ways to do this as well, too, though. If you have a lawn and you want to keep it lawn, a great way to add organic matter to your lawn is not to rake your leaves in the fall, but to leaf cycle, which basically means mow them into the lawn. If you have a, I think they call it a chipping mower, or I'm forgetting the exact term for it, but there's certain types of mowers where you only have to make one pass and it'll cut the leaves up in small enough size that you can just leave it. Other mowers, mulching mower, that's the name of it. If you don't have a mulching mower, you can still do it. You just might have to make 2 passes over the soil to break down the leaves into small enough size. What is the right size? Generally, what I've heard is if you can break the leaves down to about dime size, those little dime-sized chips of leaves will settle down between the grass blades and not smother the grass. Instead, they'll just sit there, decompose over the fall and spring, and add organic matter to your soil. You can mulch as well, too. Especially for trees, trees would much prefer to be surrounded by wood mulch than grass. The tree roots interact much more beneficially with wood mulch because mulch is in effect very similar to what these trees would be growing in normally, which is forest litter. So this is a really good example of a nice mulch ring, not a mulch volcano, but a nice mulch ring around the base of a tree. If you can extend that mulch ring out to the drip line of your tree canopy, you're going to be making your tree much happier than it would be if you had grass growing all the way up to the trunk. If you wanted to get a little more intense about it, you could do a compost top dressing on your lawn. So these are little piles of finished compost that a landscaper has laid out, and then the work crew is going to come in and rake those piles out into a thin, even blanket, about 1/4 to 1/2 inch of depth across the entire lawn. And that's thin enough that the grass blades will poke through and not smother the lawn. And eventually, over time, through the work of rainfall and burrowers like our earthworms, that organic matter, that compost is going to be incorporated into the soil within a matter of months, fairly quickly. If you're working with a really bad soil, if you know your soil is very compact, for instance, if let's say you had an old patio and you got rid of it and you're trying to do something with the soil underneath, sometimes it is best just to start from scratch, put down a lot of organic matter onto your soil and rototill it in. I wouldn't recommend this for any part of your lawn that's in pretty good shape or any part of your property that's in good shape. But if you're really starting from a very, very poor, unhealthy soil, very compact soil, sometimes the best thing is really just to till it all up and start from scratch. And by tilling, you are loosening the soil, and really, but you do want to add organic matter while you're doing this. So I recommend adding a thick layer of compost on top and then tilling that into the soil. And I wanted to show a special type of tillage that Arlington County has used quite a bit, and that Virginia Tech created. It's a method that Virginia Tech created, and they really created it for construction sites. So for that new home that's built, where heavy construction machinery has been running over the lot for the last 3 or 4 months, and the soil is in really compacted, bad shape, they have this thing called urban soil rebuilding. I call it the scoop and dump method. Basically, you take one of the pieces of construction machinery that's already on site, usually a small backhoe or a bobcat. You take the bucket of that bobcat, across the surface of the soil, you lay down a nice thick layer of compost, and then into that compost covered soil, you dig the bucket down, you pull up that soil, which is now the compacted soil down below mixed with a bit of that surfacing compost that you put on, and then you just drop it. And drop it down back into the hole you just created. And this kind of creates a swirl of compost, almost like a praline ice cream swirl of compost throughout the soil. It tends to, the dropping of the soil from height, from the bucket at height, tends to break up the big clods of soil. And over time, this creates a much healthier soil. I'm going to stop my sharing just for a second because I have a video that I want to show of a county crew in Arlington using this method. So let me pull up this video if I can. Here we go. So hopefully you can see the soil profile rebuilding website. down at the bottom, they have a link to a YouTube video. Let's see if this works. That shows the Arlington crews working at it. So there, they're scooping and dumping. Not much to it, although it is pretty labor intensive. Let me pull up the slides again.
Dan, another question.
Sure.
Can you say something about the benefits of planting native plants that will promote the soil food web more readily?
The big benefit of native plants is that they have a more extensive root system, a deeper root system than most of our ornamentals, and they are evolved to live in our current soil conditions, our existing conditions, and our existing climate. So they generally need less maintenance than some of our more finicky cultivars or ornamentals. Because they have that more robust, deeper, more extensive root system, the benefits are expanded out into a larger volume of soil than some of our smaller rooted ornamentals. So I think that's the big benefit. And, you know, they also play well with the native microbes and bacteria and such as well. So yes, oftentimes we say the best way, again, I was saying plant, that's the best way to add organic matter and to goose the soil nutrient cycle. I could revise that to say plant, natives. I don't want people to feel bad if they have an ornamental in their property, but we're kind of trying to push people into seeing ornamentals as being kind of like a dessert, if you will. People like them, they're very beautiful, but they shouldn't be the main course. You know, there's a little something that you have off on the side after the main meal. So the bulk of the plants, if they're native, and then you have these nice little pops of ornamentals mixed in with them too for a visual appeal, perfectly fine. You don't have to go entirely native, but generally speaking, the more natives you have mixed in with your landscaping, the healthier your soil is going to be because of that larger, more extensive root system and the less maintenance they need. And by maintenance, I mean things like pesticides, fertilizers, stuff like that, which can have knockoff negative effects on the soil.
Thanks, Dan.
Sure. I wanted to go through just a few. These aren't things that necessarily, I should say, these things are almost certainly not things that you would do on your own property, but some of the interesting soil tricks that counties and cities and jurisdictions and other municipalities are using to help street trees grow. And the big issue with street trees is oftentimes we're growing them in what's called the suicide strip, which is that little strip of grass between the sidewalk and the roadway. And that's a really tough place to grow anything with a big root system, because again, there's just not much space for those roots to grow. You've got compacted soil underneath the roadway, compacted soil underneath the sidewalk. And oftentimes those trees are placed into, again, a little tiny tree box, which is basically a little coffin that the roots cannot break out of. So cities and counties and towns are getting creative about ways to grow trees while also supporting infrastructure, because they've got these two competing needs. We need to have compacted soil or to make a solid base underneath our roadways and our sidewalks so that they don't collapse or frost heave. But the more compacted soil we have, the worse it's going to be for our plants. So now we're trying to figure out a way to provide the strength needed to hold up our paving, while also providing open space that will allow the tree roots to grow and expand outwards and create healthy street trees. One of the ways that communities are doing this is through something called structural soil. And structural soil is basically a mix of very angular, sharp-edged gravel and organic matter-rich soil, kind of a compost-rich soil. These angular gravel or stones are kind of used as the skeleton, if you will, of the soil. The more angular the stones are, the more they sort of catch and hook onto their surrounding stones. So you can compact these stones, but because of all those sharp angles they have, there's still a lot of open pore space between one angular stone and its surrounding neighboring angular stones. And these pore spaces are filled with that organic matter rich soil. And these pore spaces, soil-filled pore spaces, also allow roots to grow through it. If we had used rounded rocks, this wouldn't work because the rounded rocks tend to compact together very tightly and they don't have those big spaces, open pore spaces and channels between each surrounding rock. So you have to have that really angular stone that will hook onto those other stones and not compact so thoroughly, not fill in the pore spaces between the stones. This is actually an example of structural soil. It looks like asphalt because it's dark, but this is a mix of real angular stones with organic matter rich, compost rich topsoil mixed in between. They actually, this is in DC, they cut out a section of sidewalk to put down this structural soil underneath, and they're going to come back in a day or two, the work crew will, to relay the sidewalk concrete on top of it. So this is actually the sub base of the concrete. And the reason they put this down is they have this new street tree, and this structural soil will basically provide, again, enough strength that the concrete sidewalk that goes on top won't sink down and settle or crack. But there's enough pore space between those angular rocks that the roots of this new street tree will be able to grow through the angular soil, the structural soil, excuse me, and then access all of this looser, lighter, more natural soil on the far side of the sidewalk. So it's almost like a root tunnel, if you will, that allows the roots to access this good soil over here and will allow the tree to grow bigger. So it's, again, a compromise between providing enough strength to hold up the paving material while also providing enough open space to allow the roots to pass through without being blocked. A little bit more of an obvious way to do this, but an expensive way, is through something called the tree box filter, which is basically an underground vault for roots. You don't see too many of these except in newer construction, because you can imagine it'd be pretty expensive if you had an existing sidewalk or an existing roadway to dig up that existing material, excavate down 2 to 4 feet and put this lattice work in. But basically what this lattice work does is it allows the weight of the paving, concrete, or the asphalt to sit on the lattice material while also providing lots and lots of open space that the roots of that tree can then grow through. So the weight falls on the support structures, not on the open space in between. You can fill that open space with light, low density, high organic soil, and the tree roots will happily grow through it. So here is a tree box filter being installed along an existing roadway, and kind of see what the structure looks like. So again, they'll put the paving right on top of that. That I think this is a plastic substructure, lattice structure, will hold up the weight of the paving while preserving a lot of open volume for tree roots and loose soil to grow through. And then we're also beginning to see some flexible paving. And oftentimes this flexible paving is put in more as a means to lower the maintenance of walkways around big existing street trees. Because we've all seen, a tree of this size growing, sending its roots underneath the sidewalk and then pushing up that sidewalk and causing these big tripping hazard cracks. Well, this flexible paving is actually kind of a rubbery type material. It changes shape, it bends, so the roots can grow through it and they can push it up and it's not going to break. It's just kind of like a rubber mat. And actually, I find it's a lot nicer to walk on as well too, because it's a lot softer than your typical asphalt or concrete. Not exactly sure how they make it, but it's, again, just a flexible rubbery type of asphaltic coating. So just some ideas of how our more urbanized municipalities are dealing with the balance between pedestrian and roadway infrastructure and the health of our street trees.
Excuse me, Dan, we've have
Yes.
a couple more questions. Going back to your video, does it relate to the let me see if I can understand this. Does it relate to the point he made about fungi?
Not so much fungi, because this is really, in a way, you're almost inoculating the soil. So this is the urban soil rebuilding is for soil that's already been pretty much destroyed by development. So
okay.
The video that we showed was them working on that suicide strip in between the sidewalk and the roadway next to a bus stop. So the soil there was in pretty bad shape to begin with. So what they were doing was they had put on about 4 to 6 inches of compost, and then we're using the scoop and dump method to incorporate it. So you're almost starting fresh, if you will. You're taking a very poor, unhealthy soil, adding the necessary ingredients to begin a new healthy soil. But yeah, it's almost, and I'm sure there is a good bit of living soil fungi, and some of that fungi will survive the scoop and dump application method, and then they have the chance to grow from there on out. So again, I think of it more as an inoculation sort of thing, a restart to the soil.
Okay. And second question, would you put the structural soil in the hole of a street tree or just adjacent?
Usually when, again, most of the times I've seen it used, it's for new development, when they're putting in a new sidewalk, a new roadway. So they are basically putting the new tree within the structural, was you saying structural soil or within the, I'm sorry, I got confused. Structural soil or that lattice work? I think you said structural soil.
Yeah, Carrie, do you want to pipe in?
Yeah, I was curious as to whether, like, if you're just planting a street tree on your street, which I know that the soils in my health strip are really bad,
Mhm.
could you use that structural soil, the rocky angled rocky stuff in your street tree hole, or is that more for like the areas adjacent to where your street tree is growing to give it more root?
More the areas adjacent. So really what the structural soil does is that angular gravel gives the soil strength so that it holds up the weight of the sidewalk or the roadway or whatever it might be that's on top of it, while also allowing pore spaces. So I'd say within the hole that the tree is actually in, within the, the tree box, you probably just want to use regular soil, and then the structural soil would then go underneath the paved surfaces that surround it.
Got it, thanks.
Sure. Any other questions?
I'm sorry, Dan.
Mhm.
One other comment.
Sure.
A viewer wrote, please stress that some of these tactics, such as tilling, can actually destroy soil structure if it is not already in bad shape. I've seen a front yard tilled and then had sod put over the entire yard. 2 white oaks in that front yard are now declining from the loss of their roots from the tilling.
Yep. Yeah, it's really if you are starting from an extremely poor soil. So the scoop and dump method, for example, is great on a brand new construction site where everything's already been torn up. And that's actually the method that Arlington County is requesting that developers use to rehabilitate the soil before putting it on the market and selling it to the first owner. If you have maybe not the best backyard, but you got trees, you've got existing landscaping, and things are growing decently, but maybe not as well as you want, I wouldn't recommend tilling or the scoop and dump method, because it really tears things up and will destroy a lot of roots if you have root system there already. So it's really meant more for when you're starting fresh, for lack of a better term. So that's a good point.
Okay. Thank you.
You're welcome. Just very briefly, if you're interested in the soil type on your property, a really great website is the Web Soil Survey, which includes the USDA's soil maps for almost all of the country. I think there's maybe about 1% of counties that don't have a soils map, but the other 99% are mapped, and you can find all those maps on Web Soil Survey. It's a long app, but if you just go to Google or whatever your search engine is and put in Web Soil Survey, there's only one, so it'll take you there. And if you are in Arlington County, they've got a really good soils map on their GIS website, which is maps.arlingtonva.us. And I apologize for those of you in Alexandria. I just don't know their website well enough. I know they do have some GIS layers out there, but I don't know if they have a specific soils map on the county website. But you can find the Alexandria soils map on the Web Soil Survey, as well as the Arlington soil map. So those are really good resources if you want to learn a little bit more about the soil in your yard or your neighborhood. here's a clipping of the Arlington County soils map from that second URL that I gave for the southern part of the county here, south 4 Mile Run area. And that's it for me. So that's my contact information. If anybody has a question that comes to them later tonight or sometime in the coming week, feel free to give me a call, shoot me an email. I'll do my best to answer it. Master naturalists are always really good at finding me a couple stumpers. So I challenge you to ask the hard ones, and I'll do my best to try and answer them. But of course, I'll stick on for a few minutes right now too, if there's any questions that come to mind right now.
Thank you, Dan. If anybody wants to unmute themselves and ask a question, please do so.
Hey, Dan. Can you hear me?
Go ahead.
Yes, I can hear you.
Are there different types of mulch that are better than others when trying to improve soil quality?
If you're trying to grow trees, I have heard from our local Virginia Department of Forestry rep that the best mulch is what's called arborist chips, which is basically the chipped up wood that arborists create when they take down old trees. And I've heard that this most accurately recreates your natural soil mulch. One of the benefits, it's often free as well too, because these arborists are usually, the tree companies are usually looking to get rid of this stuff. Otherwise they have to haul it and pay for it to be disposed somewhere. And they were saying that some of the more shredded mulches, decorative stuff that you can find at your big box stores and your nurseries, will often over time kind of fuse together into a dense layer that can actually repel water a little bit. Whereas the arborist chips tend to stay loose and open and don't have that problem. So they allow water to more easily pass through. So the benefit of them being free and also being good for trees is what I usually recommend if you're looking for a mulch for woody, shrubby, or tree vegetation.
Dan, can I jump in on that point? This is Debbie. Hi, thanks very much. Very useful stuff. But if you have a tree that you wonder about being diseased and that's why it died, do you have to be careful not to use the chips from that tree?
I don't know. I told you, the tree stewards always find me a stumper or two. I'm not sure, Debbie. I really don't know. If I were you, I don't know what county you're in, but chances are you do have a county arborist or at least a county trees division. I think that would be a good question to ask them, because I'm really not sure.
Okay. And if there's time, I really like to go back to the question about when you were talking about how mixing the soil might disturb the fungi.
Mm-hmm.
So can you clarify though, like in a yard where, we're not, we're working with residential people and we're, turning the soil over, say, for a vegetable garden or, to prepare to plant a small tree. I was just a little more interested in understanding how we need to be careful about disturbing the fungi. And you were helpful in saying that, with the backhoe and the whole big mixing from scratch, you don't have to worry about it. But I was just a little unclear how we deal with it on the smaller scale item and be concerned about the fungi for like planting small trees or helping people with their yards.
If you're planting a tree, you got to dig a hole. There's no way around it. You got to dig a hole that's bigger than the root mass. So I'm not talking about the disturbance you need to do for planting. That's inevitable that you have to do some soil disturbance, and that's not a bad thing. It's more for, let's say, a gardener, someone who has a vegetable garden, fruit garden, something like that. The old technique was that in spring, you wanted to get this nice, clean planting bed. So you went through with your rototiller or your hand tiller or your garden claw or whatever it was, and you stirred up the first, 5 to 6 inches of soil and kind of broke it all up and created this nice, loose black soil on the surface. We are trying to get people away from that, in that, not to say that you can't do any tillage whatsoever, but if you are going to do it, maybe just a very light disking, or what we're kind of pushing people towards is growing cover crops on their garden rows over the winter, and then either mowing those cover crops down or smothering them with, wet mulch, or not mulch, wet cardboard, or even plastic sheeting, allowing them to die and decompose, and then planting right into the stubble of that old mulch. So you're disturbing the soil as little as possible, and thus disturbing the microbes below as little as possible. So that's kind of where we're going at. But if it's just for regular landscaping, you got to get the plants in the ground. So don't worry about that kind of disturbance.
Okay, thanks.
You're welcome.
So I'm sold on trying to get better soil quality and mulching the leaves, for example. But I live in a neighborhood where, first of all, there are just a whole bunch of new homes, and people move in and they put in big lawns where there used to be woods, and then they have lawn companies who come tell them what they should do with their lawn. And I have no sense of how one might begin to make them aware of some of these possibilities, and then go to the trouble of negotiating with their lawn company to mulch the leaves in instead of blowing them out. Is Arlington County making any sort of public relations efforts like that? And do you have any suggestions?
Well, I'm sure the county is. I couldn't point you to a specific website, but I know that they do promote native plants. They have some native plant sales and some free native tree giveaways as well too. I know I've taken advantage of that in the past when I had an apartment in Arlington. Oftentimes I think it's a softer approach for these kind of things is better. If you go up and confront somebody and say, hey, you're doing it wrong, that tends to make people defensive, and then they don't listen, or they purposefully go against what you just said to spite you. I think a lot of times the best way to approach these things is to lead by example. If you can get this really beautiful native landscaping, and if you do get a beautiful native landscaping, chances are you'll be attracting butterflies and other pollinators that everybody likes during the spring. People will notice. Not everybody. Some people are just not landscape folks. They want to go inside. They're not interested in gardening. But we found the folks that we work with in Fairfax who have a really nice lawn-free, grass-free front yard say that they get a lot of comments from neighbors and just people walking their dog or walking their kids to school. So you're not going to reach everybody, but I think by leading by example and having a good yard to show the beauty of natives is really the best way to, for lack of a better term, indoctrinate your neighbors into the benefits of a low maintenance native lawn, and not the highly manicured suburban lawn that we've all grown accustomed to over the last 60 years.
Thank you.
You're welcome. Okay. I think that's it. And again, hopefully you have my contact information. So if a question does come to you later tonight or later in the week, feel free to shoot me an email or give me a call, and I'll do my best to answer it.
Thank you so much, Dan. We really appreciate it.
Welcome.
Okay. Good night, everybody.
Good night. Thank you.
Thanks.
Dan